Okay, so last time we looked at power and resistors, and we saw what happened if you exceed the power rating of a resistor. It can catch flame, it will smoke, it'll ruin the component. It's never a good idea to even think about exceeding that, unless you have a destructive purpose that you're trying to achieve. So, today we're going to look at 3 exam questions that I usually give. They really test the fundamental knowledge that you should be able to pick up from the last videos. So with the first question, we want to find VA, which is the output voltage here. And there's 2 methods we can look at it. So we know that with this resistor network here, we can make that one equivalent resistor. We'll call it RT. And then we know that we would have VA right here. So now we can make a general assumption that the current goes this way. And what we can do is set up a KVL around this loop. So we can say V1 minus I times RT minus VA equals 0. And now I can really start to think about what's going on in the circuit. So we know that current would want to flow from positive to the negative side of the source. And we know that it will take every path possible. Now what we can see here is the current will come from the source through this resistor and then it gets stuck. But we know if current was flowing through here, it would be the same current flowing through RT. Well, if we don't have current flowing from this terminal to this terminal, we can say that I is equal to 0. This allows us to say that VA is equal to V1. So that's the first way of looking at it. The second way, recall that the resistance for something is given by the resistivity times the length over the area. If we want to really get a general analysis of this, we can set up the circuit this way. We have our source. Again, we have RT. And then we can just make a box and call it A. And if we want to know what RA is, well, we assume that we have an air gap here, and we know that the resistivity is equal to the inverse of the conductivity, and the conductivity for air is extremely low, which means our resistivity is extremely high. So we know that RA is going to be huge compared to RT. And this allows us to set up now the resistor divider, where we can say, let's label everything for reference. VA is equal to V1 RA over RT plus RA. We are able to factor out in RA from the numerator and denominator, and we can say that this is equal to V1 times 1 over 1 plus RT over RA. Again, we know that if RA is massive and RT is any realistic value, this term will go to 0, and again, VA is equal to V1. So there's 2 ways to do it. In this, we assumed that the distance here is fairly large. Okay, along with the distance between the terminals for VA being relatively large, we're also going to say that V1 is not something like 10,000 volts, which allows us to forget about arcing, and we're really stuck with the ideal case where VA is equal to V1, either way you look at it. So now we can look at the second question, and it's similar to what we've done before, but now we have 5 resistors, 2 voltage sources, and we want to find the current going through the first resistor. So I labeled Vx and Vy as these nodes here, based off of current going positive to negative. I said I1 goes this way, I2 goes down. For the other side, I have the current going counterclockwise, so I5 going to the left, I4 going down. And for resistor 3, we really don't know which way it's going, so we can pick right to left. And we know that KVL and KCL are self-correcting. So as long as we get the equations correct, we will get the correct answer. So first thing we can do is look at Vx and Vy and use KCL for that. So we can say that I1 and I3 are going into Vx and I2 is coming out. And for Vy, I5 is going in, I3 is coming out, and I4 is coming out. Next, we can look at KVL for 3 separate loops. The first one we can go clockwise through, and we can start with going up to here to be VA, or V1, minus I1 times R1 minus I2 times R2. The third loop will be going counterclockwise around the rightmost part of the circuit, so we would have V2 minus I5 R5 minus I4 times R4 is equal to 0. For the second equation, we will be going counterclockwise through this loop. We could go clockwise, it does not matter, but we will have I4 times R4. Remember, we get the negative sign because our current's going in the opposite direction, hence why it's positive over here. So we have I4 times R4 minus I3 times R3 minus I2 times R2 equals to 0. Now, the next thing we can do is we can substitute these two equations that we have for current into these three equations. So with the first one here, we get rid of I2. With the second one here, we get rid of I2 because we are just inserting this equation here. And then with the third equation, we get rid of I5 by inserting this equation. So from that, we can look at the first two equations, this one and this one, solve for I3, and now that these are both equal to I3, we can set them equal to each other. So then we have this equation. Now we know that I4, solving the middle equation, is equal to this. Actually, solving the last equation is equal to this. So now we know what I4 is, so we're able to plug that in right here. So we will have this part of the equation equal to this. And previously, we've seen what I3 is right here. So now we just plug this term in to I4, or I3. And we are left with this huge equation, where now we have everything in terms of I1, the resistors, and the known voltages. So we can take I1, put it to the left side, take V1 over R2, put it to the right side, and we can just divide through, and we get that I1 is equal to this very intense term. Now, we can look at a reference. So if we say V1 is equal to 5 volts, V2 is equal to 8 volts, R1 is equal to 1 ohm, R2 is equal to 2 ohms, R3 is equal to 3 ohms, R4 is equal to 4 ohms, and R5 is equal to 5 ohms. I1, or the current going through the resistor, first resistor, is equal to 1.64 amps. This really tests how much you can manipulate KVL and KCL to find a desired current. Okay, so now that we've solved for the current going through the first resistor, we can look at question 3. And question 3 is to set up as many KVL or KCL equations as you can. So we have our famous window circuit, and this will really push the limits for a freshman level student for what they can think of for KVL and KCL. So we're not asking them to solve anything, we're just asking really how many equations they can set up that are unique and useful. So the first thing that we do is we are going to label some nodes, VA, VB, VC, and VD. And what we will do, this is where we really start to bring in all the variables. So we'll call this current I2, this one I1, this one I3. Let's see, oh, this one I4, this one I5, this one I6, this one I7, and this one I8. So we can first look at VB, and we will say I1 is equal to I2 plus I3. Then we will look at VA, where we will say I2 is equal to I4 plus I5. Look at VC, where we will have I3 is equal to I6 plus I8. And lastly, we will have VD, where we will have I6 plus I4 is equal to I7. And that's as many nodes as we can really do. We can do this node, but we know it's going to ground, so we won't do that. Now we can look at two loops, which may be easy. So we can look at this loop here. Let's go counterclockwise, and then clockwise here. So with the first loop, we would have I7R8 plus I4R2 minus I5R4 plus R5 is equal to 0 because our current just has a voltage drop there. With the second one, we will have I7 times R8 again plus I6R7. It'll just be I8 R6 equals 0. Okay, so now that we've seen these four equations plus these two for KVL and KCL, we really pushed as far as we can for a freshman level class. In higher level circuit analysis classes, we would actually look at things called super loops, where we can go around bigger loops that entail other elements because we are still going around the closed path that KVL states that we have to do. So we should still have conservation. Next time we'll be going over capacitors, and that's a new component, so there's a lot more new things to learn.